In the next few videos, we're going to be discussing basic rules for computing probability. We'll start with the relative frequency approximation, then we'll talk about the classical approach, and then we'll talk about subjective probabilities. Okay, so starting with relative frequency approximation for probability. Basically what this rule says is that if we were trying to calculate the probability of, say, the event A, okay, then we can see how many times does A occur, and then divide that by the number of times the procedure was repeated. Okay, so number of times A occurs, all right, divided by the number of times the procedure was repeated. The procedure was repeated. Okay, so let's do an example where we have to calculate the probability of an event. All right, so let's do both these examples. So Fred flips a coin 10 times and gets 4 heads. Find the probability of getting a head. So I'm going to go ahead and define H. I'm going to define it very clearly. So H is going to be getting a head. So flipping a head. Flip a head. Okay, so H is my event. So I'm trying to calculate the probability of H. So let's see, how many times did heads occur? It occurred 4 times. And how many times was the procedure repeated? It was repeated 10 times. So that would be 0.4. Right. So if this isn't a weighted coin, you might think, well, the probability of getting a head, like on a 2-sided coin, is really, it's a half. So calculating probability this way, it's not so smart, right? Well, okay, let's do this next example. So what if Fred flips the coin 100 times, then he gets 47 heads? Okay, so still have the same event head. So the probability of head now would be 47 over 100. So this is going to be 0.47. Right? So what's happening here? So this is getting closer to the truth. We know that it's the probability of getting a head on an unweighted coin is 0.5, right? So what's happening is that this is called the law of large numbers. And what the law of large numbers says is that if you repeat a procedure a large number of times, so if I were to repeat it maybe 1,000 times, flip the coin 1,000 times, then we'll get closer and closer to the real probability of that event, right? So, we know what the probability of a head is, getting a head when you're flipping a coin. So this is, this is maybe not very helpful information for us, but imagine an event that you didn't know the probability of, like the probability of getting some sort of disease, right? What the law of large numbers says is that if I basically increase my sample size so that it's huge, then I can calculate the probability using this relative frequency approximation and get close to what the true probability of the disease is, okay? So as long as the number of times the procedure is repeated is very large. In that case, as long as the sample size is very large. All right, so let's do another example. This example, we have a frequency table, okay? And then we have a series of questions. So find the probability that a person has type O blood. So I'm going to define O to be the event of having type O blood. All right, so have type O blood. Okay, so now I'm trying to calculate what's the probability of O. Okay, so if I'm using this data here, let's see, I'm going to take the number of times O showed up, which is 15, and then divide that by the total sample size, total number of times we ask someone what their blood type is, right? Number of times the procedure was repeated. So what is the total sample size here? 20, 40, 50. It looks like there's 50 observations there. So 15 divided by 50. Right? You could leave the answer as a fraction, or you could go ahead and plug it into a calculator, calculate that to be 0.3. All right? So you interpret that as 30% of the population has type O blood. Right, and the law of large numbers would say that, you know, if you increase the sample size, then that probability would come closer and closer to the truth, right? All right, so let's go ahead and do the next one. So find the probability that the person has type A or type B blood. So A is going to be having type A blood, and B is going to be having type B blood. Okay. All right. So right now we're trying to calculate the probability of A or B. All right. So let's see how many A's do we have? We have 20. And then how many B's do we have? Well, we have 10. Okay. So if we add those together, then that'll be the total number of possible A's or B's, right? So that'll be 30 possible A's or B's out of the 50 in the sample. So you could leave it like that, or you could plug it into a calculator. You'll get 0.6. So you'd interpret that as 60% of the population has type A or B blood. All right. Let's go on to part C. Find the probability that a person does not have type A or B blood. So that means they have A, B, or O blood, right? If they don't have A or B, then they must have A, B, or O blood. So probability that there's, you know, not A or B, this would be equal to the probability of A, B, or O. Right? So that would be, let's see, that'd be 5 plus 15. So that is, what's 5 plus 15? That'd be 20. So let me go 20 divided by 50, which is 20 divided by 50, which is 0.4. Right. Another way that I could have calculated this is I could have noticed that, well, you know, the probability of, if I were to add up the probability of all the different types of blood, it should add up to 1, right? Total probability should be 1 here. The probability of having A or B or AB or O should add up to the probability should add up to 1, because those are all the different possibilities, right? So if I say not A or B, then that basically means anything other than A or B. So I could just do 1 minus the probability of being A or B, right? So I could have calculated this. Let me use a different color. So another way I could have calculated this is I could have said, okay, well, that'll be equal to 1 minus the probability of it being A or B. And since in part B, I already calculated the probability of being A or B to be 0.6, I could use that information, do 1 minus 0.6, and I'll get 0.4. All right, so you get the same answer either way. This way is using what we call complements, which we'll talk about more in another video. All right. Lastly, let's find the probability that someone does not have type O blood. So this is probability of not O. Okay, so since that means we could add up the probability of having A to the probability of having B to the probability of having AB, or we could just do 1 minus the probability of having O. So you could do it either way. I'll go ahead and do 1 minus the probability of O, since in part A we already calculated the probability of O to be 0.3, so 1 minus 0.3 is 0.7.